Well, hello friends. Welcome back to the program. Today we're going to continue working on the JavaScript JIT, which we've been doing for a while now. And we're just going to pick up where we left off yesterday, which was that we had just gotten Kraken, the Kraken JavaScript benchmark, kind of partially working in the JIT. We have this nice output where you can see that some function failed to compile, but a whole bunch of them succeeded. And we're in pretty good shape. We just need to keep implementing bytecodes. And I thought today the goal is going to be to get this test here to be completely green. In other words, that we would JIT compile the entire ai-astar subtest of Kraken. And that just means we're going to have to implement all of these opcodes here. So let's just get started. Okay, so we'll just start from the top today. TypeofVariable. TypeofVariable, which does. Okay, so it fetches a variable with a name and then puts the type of it as a string in the accumulator register. We can do that. In fact, let's see how we would do that. I'm thinking if we should share this code here, but it looked so simple, although sharing it's probably still a good idea. So let's share it. We'll say throw completion or value type of variable. It's probably a deprecated fly string. And then we just want to do what this code here does, except we want to return the string that we produce rather than putting it in the accumulator. So actually the input here should probably be, or no, let's do it this way. String, so we take that as a parameter, yeah. Okay, so we return this app. All right, and likewise here, just return it. Yeah, and then we can put that into common implementations. And I was thinking about this yesterday, by the way. Maybe common implementations should be a header file so that it can be inlined by both the JIT helpers and the bytecode interpreter, just to, I guess, just to allow the bytecode interpreter to have the benefit of inlining all of this stuff, some of which is pretty hot. Okay, so type of variable, yeah, it's right there. And then we just need to pass. Actually, I just need to do this type of interpreter, accumulator. That had to be in the header, sure. Okay. Type of variable, interpreter.vm. And the interpreter current executable get identifier. Is that what we want? I think so. Yeah. Cool. Yeah, and then I wanted to make it take the VM instead of the interpreter. All of these functions in common implementations that take a bytecode interpreter, we can probably make them take the VM instead. I don't think they need to see the interpreter, which would make it a little bit cleaner. Okay, so are we in good shape with that change? Let's find out. Not entirely. Oh. I am not using the local that I made there. Sure. So libjs, JIT, move type of variable. Type of variable implementation to common implementations. Then we are going to compile it. Type of variable. It's going to be one of those exciting call a C++ helper things once again. But the nice thing about all of these is that once we're done with these, we're going to be done, and then we're not going to have to do more of that. It's just a one-time thing that we have to sit through, like turning all of these into call a C++ helper output. Because after that comes all the fun fast path stuff. So type of variable value, the name of the variable, which is going to be a deprecated fly string name, I guess, or technically, name is good. Okay, and then we want to bytecode type of variable, which could throw, so we have to do try or set exception. And we just need to pass the VM and the name. Great. Type of variable. Okay. I don't think we need to load up the accumulator actually like that. No. That should be a constant with a pointer to this identifier, which we will get from the op itself. Okay, so get identifier op. Right. Have to expose that on type of variable, and then we'll be good. Maybe I should have called that identifier. That's probably slightly nicer. Okay. Right. Native call to the helper, and then put the return value in the accumulator register, check for exception, and we are good. I think that should be enough to get rid of this here. We'll see what else. This is like the very first thing that we try to JIT, which is going to be the global script context. And it now fails on SetVariable, which I guess we can implement next. But first, let's commit here. So the JS JIT, compile the type of variable bytecode instruction. Then let's do SetVariable. Actually, it's also what's blocking Go from compiling. So compiler, compile thyself. I have a hard time sometimes if I'm saying something out loud, then I really want to type it too. Like my fingers just start typing what I'm saying, which is a little bit weird. But I hear that it happens to many people. SetVariable, that's what I wanted. SetVariable, okay. Has a little bit of stuff going on, sure. I think we will, once again, yoink that out into a helper. So SetVariable, but it doesn't, at least it doesn't return anything. So it just has to potentially throw SetVariable VM and the name, let's say. And what other things do we have? We have an environment mode and an initialization mode. So let's expose those so we can see them from the JIT, and then we're going to pass the mode and the initialization mode. Yeah. Okay, and then let's take this thing. Throw completion or void. Yeah, I think we can just call them like this. VM deprecated fly string, or it was calling it name. Yeah. And then we had the environment mode and the initialization mode, which is maybe in the class. Yes, it is. Okay. And then. Sure. Oh, and we probably also want this thing to take a value that we're going to set the variable to. So I'm just going to break these up a little bit here. I'm going to put the value here. Instead of reading from the accumulator register directly, it will now just take the value that you give to it. And this makes it nice and easy to call from the JIT. So, or from JITted code rather. So let's put it into the common implementations file, and maybe now these are in op. Okay, yeah, it's a little awkward with the op namespace, I have to admit. But it's okay for now. Put it in the header as well. Oops, value, sure, and sure. Good. Does this compile? Just realized that I should have written maybe bytecode here. We'll fix that momentarily. No matching function for call to set variable. Oh, because I'm not passing the value, right? So that's the interpreter accumulator. Cool. Okay, that should then work, I think. Move SetVariable implementation to common implementations. Oh no, that's not what I wanted to do. Or is that what I wanted to do? I mean, that's okay. Why does it look so messy? I just want to reword this one. Oh no, not that one. This one, reword. Yeah. Okay. Then we need to JIT for this. So we already added that stuff, actually. Oh, dang it. I added that one line in compiler. I didn't mean to do that. Okay, let's make the commits nice. Put it back. Cool. And now we can implement it. SetVariable, which takes a VM, an identifier, and a value. That's exactly right. And also a couple of other things. So it's going to have to take, what was it, environment mode? Bytecode, op, environment mode. And I'm going to have to break this into multiple lines here as well, because it's unmanageable. All right. Come on now. And we also had an initialization mode, I think. Variable. Is that what it was? I want to say that's what it was. Okay. Oh, right, but it doesn't return anything. So we just do that. Cool. SetVariable. This becomes very simple. It's just a matter of making a native call once again with some constants. And with the accumulator loaded into arg 0, 1, 2, actually. 2 has the value, so accumulator goes in 2. The identifier goes in arg1. So you're almost good. Copilot. The environment mode, sure. We want to put that here. Oh, was that not exposed? Oh, it's just called mode. Okay, sure, whatever. And the initialization mode in arg4, sure. Call it, nothing returned, so nothing to care about, and check for exception at the end. Should be good. I wonder if, I suspect we're gonna have to handle GetVariable next. If somebody's setting variables, I would expect them to try to get them as well. But we'll find that out momentarily when we try to run with this enabled. Maybe nobody tries to get them. Okay, now we're just missing NewArray in 3 places. Interesting. Compile the SetVariable bytecode instruction. Sure. A little bit surprised that GetVariable is not there, but we'll just stick to the plan and do NewArray. So what does NewArray do? Let's look in the interpreter. NewArray, execute, create a new array, and put m element count number of values into it starting at 0. And the values for the elements are in registers starting at m elements 0. That's really weird. Start, end. What do you need the end for if you already, nobody uses it? That's weird. Seems like we only need the start, I think. Okay. And then what's going on here? Variable width. Wait, why though? New array. How do we allocate those? With extra register slots. 2. I see. So sometimes it has 2 extra slots. That's kind of strange. Probably be okay not to do that. Okay, I kind of don't want to mess with, let's not mess with the bytecode right now, although this could definitely be simplified. We are just going to compile it as is, and what that tells me is that it has a start register. I mean, if we look at what the execute function actually does, it just takes the start from element 0 and adds I to it. So that's then takes that contents of that register, puts it into the array at that index, and then puts the array in the accumulator. So it's kind of a wonky operation, but let's do it. New array. New string. Let's just put them here. Hello. It's not exactly what I wanted, Copilot, but you tried. Okay, new object. Let's just put it here. So static value, new array. Don't exactly know yet what we're going to be doing there, but we want to call a helper, and we want to do kind of what the interpreter does, but a little bit differently, I think. So first of all, we need to include array.h apparently. And then the realm we can get from the VM. Current realm. And then we want the element count. We're going to have to pass here. So size the element count, sure. We'll read out the registers. Yeah, we can get them like that. And then this here is going to be like the first register index, I guess. The register is a U32. Yeah, so first register index. Okay. And then this we can just return. And this is non-throwsy since array creation cannot fail. It's not allowed to fail. Okay, so we need to set up the arguments, which are going to be arg1 is going to be the element count. So element count, sure, and then the arg2 is going to be the first register index, which is in, what's it called? Start, I think. Start. And start will verify that you have some element. Wow, that's kind of funny. So it doesn't try to read from there if you don't have elements. Sure. That's a little goofy, but let's just work around it. So we say like, if we have elements, otherwise it will be 0, whatever. And then this thing here just won't loop if you have 0 anyway. So that doesn't matter. Okay, good enough for me. Let's see if that compiles. Ah, we're almost all agreed. We just need NewFunction. NewFunction. What do you do, my friend? You instantiate a new function from a function node kept by the bytecode instruction. Sure. Okay, so I guess we can do that. JS, JIT, compile the new array bytecode instruction. Cool. And new function, we're gonna lift that into common implementations as well. Or value, I think. Well, can this throw actually? It doesn't look throwsy. So maybe it just returns value. New function VM. What else? It wants the function node, which is a function expression, sure. Function expression, let's call it. Or no, node was fine. What else we got? I guess we'll see when we copy it over. Okay, so M function node becomes just simply, oh, so many of these, wow, look at all of them. We need LHS name, which is a optional something. Optional identifier table index. Okay. And the home object, which is optional register. Sure. Yeah, we'll figure out how to pass those as well. I guess technically we could JIT differently depending on whether those things are present. But at the moment, let's just do very generic code generation. So here we're just gonna return that. Or actually no, I shouldn't return that yet. Let's say value. Value. Here we go, and then exactly. Okay, and like that. Okay. Value is a value, sure. And then we just need the LHS name. Maybe we'll pass them like this, actually. That's probably the easiest. Because then we can just JIT pointers. Okay, so VM and function node. There we go. Beautiful. Take that, yoink it into here. Oh, this is gonna be nice. We're so close now to JITting the whole test, which is just pretty awesome. So there we go. Do you work? JS, bytecode, move NewFunction impl into common implementations. Sure. And then we gotta JIT compile it. Compile NewFunction. NewFunction. So I want the VM, I want the function expression, I want the optional bytecode identifier table index, LHS name, and what was the last thing? It was a home object. Register. Home object. Something like that, right? And bytecode NewFunction, plop. Beautiful. Compiler, compile NewFunction. And again, very simple. Let's see, are you getting this right? Not really. arg1 is going to be the function node. That is private. Okay, we need some accessors here. Okay, we're getting there. This we can take the address of, and I guess we have to bitcast it. Okay, there we go. And then same thing for all the other stuff. So we need the LHS name. Yeah, we'll just take them all as U64s like this. There we go. Ah, almost. Yes. Okay. Call the C++ helper, return value to the accumulator, and I think we're good. Now we just need to actually invoke this thing. All right. Will this be enough to run the whole test? And will the test run? We'll find out very soon. Ah, almost. Now we need PutByValue. Oh man, so many things going on there. I wonder, this is like the global execution context. So we're here. This was the TypeofVariable where we started, and then NewFunction here, presumably. And now we're doing a PutByValue, presumably after creating an array here, and then we're like shoving objects into it. Whole lot of objects actually. Quite a bit of setup time here, probably. Oh, it would be good to JIT that. JS JIT compile the NewFunction bytecode instruction. Okay, fine. Let's do PutByValue. We have PutById, so let's do PutByValue exactly. PutById. Not quite. PutByValue. Okay, let's just put it next to PutById. PutByValue. Okay. This thing probably has a bunch of stuff. PutByValue. It already uses the helper PutByProperty key, although it has a fast path here. Probably gonna put this out. Try PutByValue. Let's see, base property value. That kind of makes sense. Something like that. Okay, let's see if we can get that syntax to work for us. PutByValue doesn't, for some reason it puts something in the accumulator. Puts the value in the accumulator. Okay, I guess we can do that. I forget why. Oh, right. If I think that's like if doing a PutByValue ends up calling code because you have like a getter or setter accessor, in this case, a setter accessor that gets invoked, that means that it will execute code, which means that the accumulator could be overwritten when we get back. I think that was the reason we did that. Anyway. PutByValue. Okay. So we take the VM, we take the base, and we take a property key value like that. Storage put, oh, right, the value that we're going to put as well. Sure. Oh, and the kind. Property kind kind. Sure. Okay. Outside of that, it's very similar to PutByID, which we already implemented. So you come with us after we put mKind here. Op property kind, I guess. Yep. Sure. This is getting a little bit routine at this point, but it's okay. PutByValue. Right. Now let's go and implement it in the compiler as well. Void compiler. Compile PutByValue. Okay, can we do it? Let's see. Op base. Oh, are we not exposing those? We are not. Okay. Very good. So arg1 base property should be arg2 actually. Arg3 is the accumulator, that's the value, and then arg4 is the kind constant. Sure. Good. Native call, check exception, sounds great. I think with that, we should have everything we need to compile it. Let's see. All right. Now we are in JITted code all the way. Very cool. Okay, so let's just move that in a separate commit first of all. So like that. Nib.js bytecode move PutByValue impl to common implementations. Nib.js JIT compile the PutByValue bytecode instruction. Nice. So cool. Finally, we can JIT the whole ai-astar test. Took a while to get here, but seems like we are in pretty decent shape now with this particular subtest. So I wonder how long it takes to run it. If we just do that, just to get a little clue here where we're at. 5.2. Yeah, that's roughly the same time we had yesterday, as I recall. So probably we already had the hot parts of the benchmark already compiled in the JIT, and then today we essentially did like setup functions and stuff that was less hot in the benchmark itself. That's fine. So I think somebody asked in a comment yesterday if I could compare how much faster the JITted code is versus like compiled with 0.3. And I did the test, and it's about 15% faster than C++ compiled with 0.3 at the moment, which is nice, but it's not amazing, but neither is the JIT yet. Like we've done very, very little to optimize it. All that we've achieved really so far is eliminate the cost of control flow in the bytecode interpreter. So all of the control flow that happens when you're like executing one instruction at a time in the interpreter, all of that is now essentially gone, right? Because we instead generate the sequence of instructions that we're gonna execute. We just put them into machine code so that you can execute them one after the other without having to control flow in an interpreter. And it seems like that has gotten us 15% speed over 0.3 compiled bytecode interpreter. So cool, but I don't want to stop here because that would be little bit boring because we just did a bunch of grunt work. So let's get a little call grind capture of this test, and I think this is going to take a while, so I don't necessarily want to run the complete thing in call grind today, but because it would probably take a couple of minutes. But I think if we just let it run for a moment, we will probably get a very interesting sample still of where is the time being spent and how many, which particular C++ native call helpers are we ending up spending time in, because those would then make great candidates for FastPath and inlining. So this, at least now we know that it's compiled all the functions. So let's just stop there and maybe just cache grind, cook cache grind on it. So, okay. So what do we got? We can see that get by ID, pretty much very, very heavy. In fact, we can probably do like cxx underscore. Yeah, so this shows us like all of the cxx helpers for the various opcodes that are now eating up time. So call, of course, is very heavy on the inclusive, but its self time is low because function calls are parents of things that are hot, but are not themselves hot. The hottest thing here that I see is ResolveThisBinding. So with about 9% inclusive, this particular opcode is, at least from what I see here, the heaviest. So we can try to make that one faster right away. The easiest way to do that is probably to add a to cache this value, because this cannot change inside of a JavaScript function. Like once you have learned this, it's not going to change after that unless you're in a different function. It doesn't change within the same function. But it can't throw when you try to get it, as we talked about in a previous video. But it's not going to change. So what we do in the interpreter today actually is we do cache it in the interpreter, resolve this binding. The cache this value is stored in one of the VM registers, the this value register. So we can teach the JIT code how to use that cache. That would probably save us quite a bit of time if we're looking at almost 10%. Let's call it 9% of runtime being spent in the resolve this binding thing. And then I think this is sort of how we can approach JIT optimization in an interesting way going forward. Like you can run a test and then you get a list of these opcodes, see which one we end up calling into C++ for, and then look at the inputs to that thing, figure out like, oh, how can we write inline assembly to cover this case? And of course, is it a good idea to do that? Like, or is this would it be like a benchmark specific optimization, blah, blah, blah. But in this case, resolving this binding for sure is a generically useful optimization. So let's do that. Let's see, so resolve this binding. Right, so what we do currently is we just do a native call to the C++ helper, which does no caching or anything. So you could do caching in the C++ helper, but let's take it a step further and do the caching stuff in inline assembly. So I think we can just load VM register. We'll load it into GPR0, and we have it in this value. And if it's empty, then we know that it hasn't, like the cache hasn't been populated yet. So we have to compare it to empty. And I think the easiest way to do that right now is to just load empty into another GPR, put an empty value into another general purpose register and then compare them, basically. So assembler jump if they're equal, these two registers, then we have to jump to like a slow path, slow case, let's say. And we will make a label for that, and we will link that label down here. So basically, if it is empty, we will jump to the native call. If it is not empty, then GPR 0 contains the current this value. So we can just put that in the accumulator and we're basically done. So load or store VM register rather. Store VM register, accumulator GPR 0. Yeah, thank you. And then we want to skip past all of this stuff. So yeah, I was going to say, let's make a jump to the end. We'll call it end, and then end link to here. Cool. So optimization, we cache this value in the in the register, this value register in a special register. So first we check if the cache is non-empty, and if so, let's say, and if so, we can avoid calling out to C++ at all. So I think this is sane. Let's see, what are we doing? So we're loading this value, the cached this value into GPR 0, loading an empty value into GPR 1, and then if they are equal, GPR 0 and GPR 1, we jump to the slow case because then it is empty. The slow case, we can also call it like uncached case or something like that. I don't know, slow case is pretty understandable to me. So this is the fast case. We have a cache this value. Yes, that's exactly what I wanted to say. Cool, thank you, Copilot. Right, store it in the accumulator and get the heck out of here. See, we're gonna skip all of that stuff. Let's see how that works out for us. Okay, and let's just try running it right away again. Does it get any faster? It is slower. Why is it slower? Very suspicious. Oh, maybe it's slower because we never set the register. Ah, of course. So we're just strictly doing more work now. So we do that. And here we have to set it. So like bytecode interpreter reg, this value is this value, yes. So after we've called this thing once, we've now set up the cache. Yeah, right, because nobody else is setting up the cache for us. So if we do that, then now we are noticeably faster. We're down from, what was it before, 5.2? Something like that, down to 4.8. So that is a very respectable improvement from a little like inline assembly fast path, right? How cool is that? So I would imagine that if we were to grab another call grind profile here, we would see the CXX ResolveThisBinding just completely gone from the leaderboard, and or like not completely gone because it will be sad at the bottom, but multiple. You can do any number of subsequent calls to it, and they will just hit the cache as long as you're inside the same function. That should be very nice. Yeah. Makes me wonder if there are cases where we could pre-populate the this value register, like when setting up a function call itself. If you know what this value is going to be, you could poke it directly into this register while you're at it to make the operation fast, although that seems like it might be a little bit tricky with some edge cases. So definitely would have to be justified with numbers if we're going to do stuff like that. But there's way lower hanging fruit than messing with that kind of thing right now. So let's just break there. And what did we record? 1107, sure. And cxx underscore. Look at that. He is no longer in the top. He is down here. So down from like 9.3% to 0.02%. Still has a number of calls. He's still calling it 30,000 times, but way less than before. Right. So that's pretty awesome. That is really awesome, actually. Let's just commit that. Lib.js, JIT, add fast path for cached, resolve this binding fast path for the resolve this binding cogen. Now generate inline assembly or a fast path for cached this values. The first time this is resolved within a function, we call out to C++, but then all subsequent requests or accesses are cached. Will hit the cache in reg and register this value, let's call it. Cool. That's super cool. And yeah, so in order to make this test go faster, I think one strategy is going to be to improve these guys and give them fast paths. So like abstract equals, which is non-strict equality. So the equal operator, not the equal operator. And we got get by ID. This thing is going to be interesting to optimize. Ultimately, we probably want to JIT compile a fast path for inline caches, so that if you have an inline cache hit for a get by ID, you can stay in assembly code. Increment, again, we can do fast path for some of the value types, like int32 for sure. Less than, very same as increment. Like if you're comparing two integers against each other, we can have fast path. To numeric for things that are already a number could be a fast path. Get by value. Yeah, like all of these things we can come up with fast paths for. And it will be interesting to do that. If we look at the whole profile, what do we see? Get by ID is very, very high. It's higher than the CXX thing made me think. That's interesting that it's almost 25% of runtime now. Yeah, so inline caching in JITted code is probably going to be very valuable as well. Anyways, there was so many things to do, but I think this first thing was a nice and easy example of an inlining optimization we can do. So let's leave it at that one for today. I wonder if we have become able to run any other tests, by the way. I've just been doing this one Let's try some other ones, like beat detection. We still have stuff to do. We got GetVariable. Sure. And what else was I trying yesterday? Like imaging, dark room, let's say. That one we compiled the whole thing. That's awesome. So I wonder, just out of curiosity, like how fast are we on that thing? It runs in 5.2 sec, sure. And we can test it without the JIT also, just to get a feel. .5, look at that. Yep. Very cool. And, you know, every test is going to have its own things that we can make faster. And it's going to be a lot of things to discover, things to learn. And the code that we're spitting out is itself not optimal. Like we can do better, much better instruction selection. We can find ways to eliminate redundancies. There's all kinds of stuff we can do, but got to start somewhere. So we have started here, and it is looking pretty cool. What's the last one I was trying to do yesterday? Like one of the crypto ones, AES, right? Yeah, I think that was the one. Oh, right, libjs. Okay. Compiling almost the whole thing. GetVariable is pretty popular. Maybe we can just throw together a GetVariable real quick, because maybe that will actually unlock a bunch of other tests. So GetVariable, let's just do it. SetVariable. GetVariable execute. Not inline caching and stuff. All right, no. I should stop here. I'm gonna stop here. I don't want to deal with that right now. So yeah, let's end it. It was we've done a good portion of stuff today. We implemented enough compiler stuff in order to JIT compile the entire ai-astar subtest. So we can now run one of the Kraken subtests completely JITted. That's fantastic. Then we did a very quick performance check with call grind and found some interesting optimization targets. We did ResolveThisBinding fast path for cached this access, and it was noticeably faster. We went from 5.2 seconds to 4.8 seconds average runtime for the test. And that's awesome. That's really cool. It's a substantial improvement for such a small thing. And yeah, kick ass. Yeah, I think this is going to be the end of the video. So if you made it here, thanks for watching, for hanging out. I think this series is really fun so far. I'm really glad that we're still doing it. And I'm really happy that I managed to like put all the programming in videos this time and haven't worked on it like outside of the videos. So you can see the whole thing get built in this series. I think this is the first time that I've managed to do that since the bytecode VM that I did 2 years ago. And even then, after I published the initial like drop Netflix season for that one, other people started helping out. But here I've been staying in a branch just to allow this work to sort of happen atomically. And obviously this is going to go into the main repository at some point, but it's really nice to be able to tinker and flesh it out like this. So I've really been enjoying that. I hope you've enjoyed watching it, and I think we're going to do a little bit more, a couple more videos at least of just fleshing things out more and adding more fast paths, probably working a bit on the ergonomics of writing JIT code, because it does feel a bit clunky to do some stuff, but all in good time. Anyways, thanks for hanging out today. I will see you next time.